Hi, this is Mrs. Robel. This is part 3 of periodic table and trends in the periodic law. So we're going to round out talking about ionization energy, the formation of ions, and why are some ions more stable than others. And I wanted to show you the periodic table here, and more specifically the transition elements in the last two columns, copper and zinc. Remember, we have in this section here the anomaly with electron configuration. So we end up having one electron in the 4s orbital, and then we have essentially 10 electrons in the d orbital. And this diagram that I want to put up here, notice that the 4s energy level is pretty close to the 3d energy level. So when you ionize copper, silver, and gold, and you remove one electron, it's going to be actually lower in energy than if you were to do it in the zinc, cadmium, and mercury family, because they have both full orbitals in the s and the d electrons. And when you have electrons with opposite spins, you have a little more resistance to removal with that electron. So essentially what that means is that when we're looking at copper, silver, and gold, they are going to have a lower ionization energy, and that's because of the s orbital with one electron in it and a full d orbital. Whereas if you look at the ionization energy of zinc, cadmium, and mercury, they have both a full s orbital and d orbital, so there's more resistance. It requires more energy to remove that last electron in that family. Okay, now I want to look at formation of ions here. So if you notice on the left of each ion is a gray color, and that gray color represents the neutral atom. So notice that on this section where you see red, we're talking about cations. So group 1 through 3, we're talking about the formation of cations. So notice that that section of the periodic table, we have more metallic character, so they're more readily able to give up that extra 1, 2, or 3 electrons. Now notice that the size of the cations are actually significantly smaller than the neutral atom, and that makes sense because you removed electrons. So you're stripping away that outer layer of electrons. And notice as you go from the first group all the way to the third group, the differences, they're a little more dramatic, like halfway. And remember, you're increasing the positive charge of the nucleus. So those electrons that are around that increased positive charge are more tightly held. So the radius should be smaller for that group 3 cations. Now the opposite happens when you have anion formation. So the blue is essentially anion formation. And when you're looking at anions, you're adding another layer of electrons. And notice that the neutral atom is in gray, and it's smaller than the anion. So that makes sense because we're adding electrons. And notice you go from 1 to almost 2 size doubling of the anion. So you're adding that extra layer of electrons. And notice for oxygen you need to add 2 electrons, sulfur 2, selenium 2, tellurium 2. Whereas with group 7 you're only adding 1 extra one. So the increase isn't as significant. Okay, so when we're looking at the formation of cations, notice that the outer electrons have been removed. So as the outer electrons have been removed, they're in a lower energy state. So you see a compaction or a formation of a smaller ion. You have fewer electron repulsions. There's less electrons to go around, so you don't see as much spacing out of the electrons because of that. When you're talking about formation of an anion, something else is going on. So instead, the radius has to increase because there's more electrons. And when there are more repulsions, there's more electrons, we get a spreading out of the anion. Okay, so this is a general trend of the alkali metals. So notice that when you're looking at alkali metals, they tend to be the largest atoms for their period. So on the left-hand side of the periodic table, we're talking about the largest sized elements. Notice they have the lowest ionization energy, and that's all because they lose that one electron and they essentially form a positive ion charge. They are the most reactive, so hopefully I've done a demonstration for you. If I haven't, you should bug me about it to show you what happens to alkali metals. Notice that as ionization decreases, reactivity increases. So if the sky was no limit and we could get our hands on some francium and threw it in some water, some very interesting things would be happening. So something to keep in mind with reactivity. Okay, for halogens. Halogens, it's a little bit different. They are very tiny, and remember, they're small because there's a higher positive charge in the nucleus and there is electron affinity. So they're drawing in their electrons as tightly as possible. They're more closely held to the nucleus. You're gaining an electron to form an anion and a negative charge. They are the most reactive out of the metallic family. I'm sorry, non-metallic family. So when we're looking at a reactive non-metallic family, as electron affinity decreases, reactivity decreases. So this is a little bit opposite of the alkali metals. Notice if you want to get your hands on some fluorine or some chlorine, you're talking about a more reactive nonmetal. Okay, noble gases. So noble gases, you're probably most familiar with them in neon signs, okay? They have the highest ionization energy. They tend to hold on to their electrons very tightly, and because of that, they are not willing to give them up. They have zero electron affinity. They are not interested in acquiring any more electrons. Because of that, they are called noble gases. They're very stable. You have to really put energy into a reaction or perturb those elements in order to get them to react with other elements. Okay, here we go. These are some questions, and I'm going to answer some of them, and I think one I'm probably going to leave for you to decide. So the actinide series, is it part of the S block, the inner transition, nonmetals, or alkali metals? Okay, very good. So inner transition, that's the very last 2 rows of the periodic table. I'm sorry, it's part of, yeah, you know what I was saying. Okay, for the element state, which group has the complete octet of valence electrons? So is it alkali, alkaline earth, halogens, or noble gases? Yay. Okay, so noble gases, we just talked about that. Okay, which block contains transition metals? Is it the S block, the P block, the D block, or the F block? Excellent. Okay. All right. I'm going to let you answer this question on your own, and don't be surprised if you see this with the next video assessment.